Hello, everybody. Welcome back to another Strengths of Materials video. This one is on compound beams. It's super easy, super simple concept to explain. We're going to do a super easy problem as well, just to kind of go over the details of what we need to do for problems like this. Um, Really, it comes down to like the basics of equilibrium equations. We have the three that we have, obviously, is f of x, f of y, and the summation of moment. We set them all equal to 0. But the unique thing about these types of problems is that they give you a compound beam, which is pretty much just saying that you have a beam that has been segmented by these connections that are scattered along its length. And what this allows us to do a lot of the time, if you have a idealized pin connection at these locations, then we can do some unique things with these beams for analysis purposes. Because typically, this would be considered an indeterminate beam to solve for if these connections were not here, because we have a fixed connection and two supports, meaning that we have 5 unknowns, but we only have those 3 equations that we were talking about earlier. However, this problem is going to show us why these pins are so important, which allow us to solve problems like this. So in order to explain that, we should probably hop into the problem. But the key takeaways before jumping into it is just to understand that at these pins, if you imagine that you had this force being applied, this pin is going to be taking a reaction or taking that load and causing a reaction at this pin. And let's say that this reaction is going to be 5 kilonewtons in the opposite direction. That means on the other side, in segment BD, you're going to have an equal and opposite reaction being created in the adjacent segment. And that's going to make a lot more sense when we isolate each of these individual segments. Another important one is that at these pins, there's no moment being produced here because there is the freedom to rotate. I don't know if you can see it very well in this drawing, but you can imagine that you have gaps that are in between these pins that allow the beam to rotate and almost deform as you are causing this kind of flexure throughout the beam. Meaning that at these points, you are given that freedom to rotate, meaning that no moment is actually developed there. And the last one, obviously, we talked about this. We have these individual segments. What these pins allow us to do is to isolate each individual segment into its own free body diagram. So I've labeled these as I, and I, for lack of better naming convention, or you can call them 1, 2, 3. And we can see each of the individual free body diagrams in the next part of this video. Alrighty, so now you can see all the individual segments of the beam split at the point where the pin is connecting each adjacent segment. So we have AB, we have BD, and DE as each individual free body diagrams, which is step 1 to solving this problem. The next step, which I've gone ahead and done for you guys, is just figure out what reactions you have in each of these beams. So we have a fixed connection at the end here for AB, meaning that we're going to have a moment. We're going to have a lateral AX and a Y reaction labeled AY. Then similarly, you can label the pin with a Y and an X reaction. So BY and BX, which are labeled here, giving us with a total of 5 different unknowns that need to be solved for in this beam. Moving on to the next one, it's a very similar thing, except we have 2 pins and a roller. And at the pins, we have the X and Y components respectively. And we have the Y reaction from the roller. No X reaction here because it is not a pin connection, so it's allowed to laterally move both ways. And the last segment is DE. We have the X and Y for the pin once again. And you're going to notice that point that I've brought up at the start of this video. Each of these pins is producing equal and opposite reactions in the way I've drawn them currently. So you can draw these reactions in any way that you think is going to be right prior to solving the problem, but you just need to be consistent when labeling your diagrams to ensure that if you draw dy, for example, going in the positive direction, on the adjacent segment, it has to be in the opposite direction. That's the same for dx in this case, and all of the other pin locations here. And yeah, last segment has a y reaction here at the roller, and that leaves us with the question, how do we begin solving? Well, the way I like to think about it is which element has the least amount of unknowns. So element 1 has 5 unknowns, element 2 has 5 unknowns, but element 3, we're actually left with only 3 unknowns. So that gives us some opportunity to work with this beam here to figure out some of the unknowns and then work right to left in order to solve the other segments. So let's go ahead and start solving segment 3. I'm just going to label it at the top here. And the only way that we can proceed with doing this right now is to take the summation of moment about point D. Why is that? That's because we're going to eliminate dx and dy from that first equation that we're using because they act at the point of reference for our moment. There's no arm or length to these distances, meaning that the only unknown will be the EY. But we also need to consider the influence of the 10 kilonewton load, that is 1.5 meters from that reference point. So let's say that we're taking the summation of moment about point D, setting that to 0, and picking our sign convention. We are going to have 0 is equal to the first external force we run into, which is negative 10 kilonewtons, and that is 1.5 meters away. I made it negative because this is going to be creating a clockwise rotation based on our convention here. And then similarly, you do the same thing for EY, except this time you're creating a counterclockwise rotation about D, meaning that you're going to have EY, which is positive, and then that is 3 meters away. So 1.5 plus 1.5. Solving for EY, you're going to be left with 5 kilonewtons. What's next? Now we can go ahead and solve for the other Y reaction, because now we have only one unknown Y in this problem. We can go ahead and do summation of force of Y equals to 0 and plug in what we have. We have dy, which is drawn as a positive, the negative 10 kilonewtons, and then the EY, which has been solved as positive 5, meaning that it was drawn in the right way in our drawing. So we can add positive 5 kilonewtons for that EY, bringing the dy over and solving. You're also going to be left with 5 kilonewtons. Then since there's no x forces externally applied, we know that dx is also going to be 0. So now let's carry these forces over. Go ahead and start solving for the second segment. Okay, our drawing is now updated with all the forces that we just solved for in segment 2. Now we can go ahead and figure out what the unknowns are for this specific segment. And we're doing a very similar thing once again. We're taking that moment about B, because we have 2 unknowns here that are going to be canceled out as soon as we take the summation of moment about this point. And then the only unknown is going to be that C reaction on the roller. And you can see the equal and opposite reactions being applied at the pin D. So we had 5 kilonewtons upwards here. It's now going to be acting in the downwards direction in the next segment that we're looking at. So let's go ahead and do the exact same solving process, except now we're taking the summation of moment about point B. Alrighty, so everything's plugged in for this first equation. We have Cy, which is 1.5 meters away, the external moment being applied in the clockwise direction, meaning it's negative, and the dy reaction, which is 3 meters away from our reference point, meaning that Cy is going to equal 16.67 kilonewtons. And once again, going on to the next part, which is summation of forces at Y equals to 0. We have the only one that we don't know right now, which is negative By, negative because that's how I've drawn it or assumed it in this problem. We then add the Cy reaction we just solved for, 16.67 kilonewtons, and then the dy, which is negative 5. Let's bring the By over and solve for 11.67 kilonewtons. And once again, obviously, Bx is going to be 0. There's no external x forces. So we can go ahead and finally solve for the last segment, which is segment 1. Okay, drawing's updated again, and we are going to do the exact same thing. You guys know the rules by now. We're going to be taking the summation moment about A, just to get rid of those 2 nasty x and y reactions there. We are going to be left with an equation that looks like this. We have to first consider the moment at A being produced. Since it's a fixed support, it is drawn in the clockwise direction, meaning that it's going to be negative based on our convention. Moving along, you have the external 9 kilonewton force, which is also creating that clockwise rotation. That is 1.5 meters away. And you have the By drawn in the opposite direction with respect to segment 2, and that is going to be creating a positive rotation, or a counterclockwise rotation. Sorry for my French there. Counterclockwise rotation, which is 3 meters away. Then solving for MA, you are left with 21.51 kilonewton meter. And very simple stuff, guys. Summation of forces at Y. Taking that equation and figuring out what that AY is. So first we have negative AY as we've drawn it, the negative 9 kilonewton from the external reaction, or the external force, sorry, and the reaction at B, which is positive 11.67, leaving you with your final unknown for this problem, 2.67 kilonewtons for AY. AX is going to equal 0. And you can plug this into your drawing for a nice, clean little picture for the end of this problem. That's it. Super easy stuff. I just hope you understand the concepts of what's going on with these pins and what needs to be done to analyze each of these individual segments. Hope this helped. Thanks for watching.